Hey everybody, Mr. Johnston here again. In this part of the video, we're going to talk about how to determine cell potential for a voltaic cell. So just a quick recap from what we talked about before. A galvanic cell consists of a substance being reduced in one cell, and that pulls electrons through a wire from a substance that's being oxidized in another cell. And so another word for galvanic cell is a voltaic cell that we talked about in the previous video. This pull, or this driving force of electrons, is called cell potential. And we can actually calculate cell potential in a galvanic cell if we know the reduction potentials. The unit of electrical potential is called a volt. A volt is just a unit of work that is equal to 1 joule per coulomb of charge being transferred. So thinking about like how much energy or how much electrons are going to be going through that wire. It turns out that there are ways of measuring this cell potential. And almost every chemistry textbook has a list of standard reduction potentials. This is a list from a textbook. Our textbook has this same chart. It's actually in chapter 19. It's table 19.1 in our textbook. But the way that these are set up, each one is a reduction reaction. The things at the top of the list are most likely to be reduced. They are the ones that are gonna produce voltage in the reduction process. The ones at the bottom of the list are most likely to be oxidized, and so they actually have negative reduction potentials. And we'll take a look at how to use these values from this table when we go through an example from our guided reading. So all half reactions are shown as reduction, and they're standardized, so that's why they're called standard reduction potentials at 1 molar, 1 atmosphere, and 25 degrees Celsius. When a half reaction is reversed, then the sign of the potential is also reversed. So if we know that something is actually oxidized, then we just flip that reaction and reverse the sign of the cell potential. In any redox reaction, the number of electrons lost has to equal the number of electrons gained. And so sometimes you have to multiply half reactions in order to balance the electrons, but this does not change the standard cell potential. Here's the other thing, is the direction of spontaneity gives a positive cell potential. So the spontaneous reaction is always going to have a positive cell potential. The way that we calculate the cell potential is you take the potential of the cathode, and that's the redox or the reduction portion, plus the anode, which is the oxidation portion. And again, we'll look at some examples of how to do this in just a couple of minutes. So that equation, E cell, is equal to the reduction potential plus the oxidation potential. So the work done by a galvanic cell, we already mentioned this, but work can be accomplished when electrons are transferred through a wire, and it depends on that push-pull idea behind the electrons. That's the cell potential. This equation is on your AP reference sheet, and this equates Gibbs free energy to that cell potential. And remember, a spontaneous process always has a negative sign for Gibbs free energy. So if you think about this, if you have a positive cell potential, then you're going to have a negative Gibbs free energy. The other terms in this, N is number of electrons, and that's the coefficient from the balanced equation, how many electrons are transferred. And F is something known as Faraday's constant, and that's a constant given on that AP reference sheet. The main thing from this equation is that if cell potential is positive, then it's a spontaneous reaction because that'll make Gibbs free energy negative. In the next part of this video, I want to take a look at some examples from your reading guide. And so on our reading guide, I'm on the top of page 7 here. And first, we just want to determine whether the reaction is thermodynamically favorable in the forward direction. In other words, is it spontaneous? Or in other words, does it have a negative delta G? And so what we want to do is we want to first decide what is being oxidized and what is being reduced. Anytime you have an ion going to a solid, remember ions, the oxidation potential is the charge of the ion, or I should say the oxidation state is the charge of the ion. For an element, the oxidation state is 0. So in this case, the calcium ion is being reduced, and the zinc ion is being oxidized. Now, the next thing that I want to do is I want to look up those cell potentials and see where they are on my list. And so I'm going to pull out my textbook here, and I'm going to find each of these things on my list of cell potentials. This is table 19.1 from our textbook. So each one of these, by the way, is listed as a reduction reaction. So let's find those couple that are in our first example, calcium and zinc. So scanning through. So here's calcium. It's actually way towards the bottom. So I'm going to put a little asterisk next to calcium. So this is calcium being reduced. And here's zinc. Now zinc is being reduced in this equation. In our example, we said that zinc is oxidized. So what I'm going to do is I'm going to take and reverse this reaction. So on my chart, if we write this out, oops. So the zinc half reaction is Zn is going to make the ion plus 2 electrons. That is the oxidation reaction. Now, in our textbook, we get not an oxidation reaction, but a reduction reaction for zinc. So again, I'll find zinc. And so this is the reverse of the reaction, so we actually have to take and flip the sign. So it's a positive 0.76. The reduction reaction for calcium is the ion calcium plus 2 electrons makes solid calcium. And again, looking up in my textbook, way on the bottom here, here's calcium. And so that is the reduction reaction. Its potential is negative 2.76. And so now what we need to do is simply add these two numbers together and see if it's negative or positive. So if I put those two numbers together, it's going to be negative 2.00. And so coming back to this equation from our AP reference sheet right here, delta G is equal to negative NF, and this E is cell potential. So if we have a negative cell potential, it's going to make Gibbs free energy positive. And so for this one, it is not thermodynamically favored. Because you have a negative cell potential. The equation that we use to determine cell potential, I mentioned in the first part of the video, but it's worth writing down in case you haven't already. It is the first reduction potential plus the oxidation potential. And the thing that we have to remember is when we look up these numbers from the chart in our textbook, all of these are reduction reactions. And so once we determine which one is oxidation, what we're going to do is take and flip it, and we'll end up flipping the sign on these cell potential. Let's take a look at part B here. So I'm going to start again by identifying what is reduced and what is oxidized. And then I'm going to come over to my textbook and I'm going to find those two reactions. So the reduction reaction is silver. And if I look on my chart here, here's silver. So silver's reduction potential is 0.8. Now I'm just going to make that note right here next to the reduction number, and that was a positive 0.8. Now the nickel is being oxidized, so let's find nickel on our chart. Now the nickel is being oxidized, and its potential, this remember is a reduction potential, so I'm always going to flip the one that's being oxidized. The reduction potential is negative 0.23, which means the oxidation potential is positive 0.23. And then once we are looking for, is it thermodynamically favored, we're simply adding these two numbers together. That's going to give a standard cell potential of positive 1.03. So if it's a positive standard cell potential, then it's going to be thermodynamically favored. I'm going to let you pause the video right here and work through part C and part D and see if you can decide if those are thermodynamically favored or not. So here's what I got for letters C and D. One quick note is that the iron, there are several reduction reactions listed for iron. So be careful on which one you chose. We're, in this case, looking for the iron 2+ ion. And of course, they're listed as they're listed as reduction reactions. So on this example for letter C, we're oxidizing the iron. And so you're flipping the sign from compared to what you saw in your book. So I said C is not thermodynamically favored because it's got a negative cell potential. And D is thermodynamically favored because it has a positive cell potential. All right, now we're going to take a look at how we can do these problems from our reading guide packet, where we're going to sketch out the voltaic cell and write out both the cathode and anode reactions, and then finally figure out the cell potential. So this is a good one for us to do together, because I know it says to look in table 9.1 of our textbook, but when you do, you'll come up short on finding cobalt, because for some reason cobalt is not listed in our reference page for these standard reduction potentials. I looked it up in another source and found a standard reduction potential for cobalt is -0.28. Silver is in our textbook, and so for when you look up silver, you're going to see that it's +0.80. And so based on those values, we know that silver has a greater reduction potential. And so this is going to be our reduction reaction. That means the silver is going to be reduced, and the cobalt is going to be the thing that ends up getting oxidized. We always put the reduction reaction on the right and the oxidation reaction on the left in our diagram. And the reduction reaction is the cathode reaction. So as we said, that's going to be the silver. So the silver is going to get reduced. And that's going to make cobalt is going to be the thing that gets oxidized. Now, the overall reaction, look at here, the silver is gaining 1 electron in that reduction, whereas the cobalt is losing 2 electrons in its oxidation. And so when I write the overall reaction, I've got to pay attention to the number of electrons. So it turns out that 2 silver ions, and each silver ion is +1, is going to react with 1 cobalt to make 2 silver atoms and 1 cobalt ion. Now, when I go to sketch this, again, the oxidation, so I would draw my piece of cobalt metal right here. I'll label that. And in my solution, you're going to want some cobalt solution with cobalt ions. So maybe cobalt nitrate or something. And then over here on the reduction side, you're going to need a piece of silver metal. And you're going to need silver ions in this solution. We're going to connect those with a wire. And you might want to put something like a voltmeter or a light bulb or something in between those. And then we are going to need a salt bridge. You always need that salt bridge to close the circuit. Now, in terms of, we wrote out the half reactions, in terms of the overall cell potential, even though we had to put a coefficient of 2 in front of the silver, it does not change this standard reduction potential. So this is still 0.80. And we looked up the reduction potential for cobalt, but we realized this is the thing that's oxidized. So that reduction potential, since it's an oxidation reaction, we flip the sign, which means that the overall cell potential is going to be positive 1.2, or sorry, positive 1.08, and that's volts.